Can you hear me? I hope so. My name is Karol Życzkowski. I work at the Department of Theoretical Physics at the Jagiellonian University in Krakow. I have a great pleasure and honor to introduce to you the first speaker, in fact, the last speaker of today. But before, let me thank the organizers, not only for organizing the conference, but also for taking into account a community of mathematical physicists, for allowing us to organize quite a few sessions related to Hamiltonian systems, methods in Hilbert space, operator theory and theoretical physics, and last but not least, numerical ranges and quantum information. It's really very encouraging for us to see that several mathematicians got inspired with problems motivated by theoretical physics, quantum physics, and there are really a lot of nice mathematical results, obtained rigorous results, which are important, interesting for physicists. And therefore I can introduce to you Ion Nechita, originally from Romania, got his PhD in France, in Lyon. That was a postdoc in Canada, in Ottawa, also in Germany. Now he's back in France, in Toulouse. And he had obtained a lot of interesting results concerning random matrices, concerning applications of operator theory in quantum information, concerning bounds on entropies. And today we'll learn from him about applications of spectrahedra in quantum information theory. Ion, please, the floor is yours.
Thank you very much for this very kind introduction, Karol. And thanks to the organizers for giving me this great opportunity to give a plenary talk about some of my work. It's really an honor to be at this very nice conference. So maybe I should start by saying that this is joint work with Andreas Blum. So we are now both researchers at the CNRS in France. And so this project started actually tell you a story, but it started in IHP in France, in Paris, during a quantum information theory program. And at that time we had 3 months, so we had some free time. And we were reading a paper of Bill Helton, actually. So this is maybe the first connection to IWOTA. This paper I'm going to tell you about, it's called Matrix Cube Dilations, and it's become a book now, so it's published in the Memoirs of the AMS. And when reading this paper, so it was about, at some point, positive and completely positive maps. And in quantum information theory, this is, there are many things which can be expressed in terms of positive and completely positive maps. So we said maybe there is some connection, and indeed there is a connection, and that's what I'm going to tell you about today. And so it's like this project has been going on for 5 years now. There are many papers. Here are some of them, the archive links. And today I decided to tell you about maybe the easiest way to connect these two fields, quantum information and this free convexity. I mean, it has many names. This new field where free spectrahedra appear. So good. So let me first give you a snapshot of this talk. So what is the story behind these results? So the goal is to tell you about this connection between these two fields, which a priori have no link one to the other. And so the first of these fields is quantum information theory, and like a particular part of it, which is called compatibility or incompatibility of measurements. And the second topic is about free spectrahedra. So I will tell you about these geometric objects, spectrahedra, and their matrix versions, free spectrahedra. And basically our point of view. So at that time we are working in quantum information theory. So what we did at first is, once we established this connection, we looked at the literature about free spectrahedra, and we saw that mathematicians had proven many results, and we studied these objects thoroughly. And then using this connection, we could get some new insight in quantum information theory about measurements and their compatibility. And later we realized that this connection goes the other way around. So using ideas from quantum information, like really physics-inspired and information theory-inspired ideas, quantum cloning, such as quantum cloning, we're able to get some new results like in pure mathematics, if you want, in this theory of free spectrahedra. So basically, this is the one slide story. Now, here is an outline of my talk. So since, maybe not all of you are familiar with quantum information theory, I will give you a brief outline of this problem of compatibility and incompatibility in quantum mechanics. So that's, the first part of the talk. Then I will tell you about spectrahedra and free spectrahedra. Like this will be two very disconnected sections, and everything will come together in the third part, where I will tell you the connection between these two objects. And then finally, I will tell you about some what are some proof ideas. Okay. Good. So first, incompatibility in quantum mechanics. So this is first part of the talk. It's about quantum information and quantum mechanics. So here's all you need to know about quantum theory for this talk. So you may all know that in quantum mechanics we associate to a system a Hilbert space. So all Hilbert spaces in my talk will be complex and finite dimensional. So things are easy. And a quantum state is just a unit vector inside this Hilbert space. And usually I will my Hilbert spaces will be of dimension d. So d will denote this dimension of the space, finite dimensional. And so you have this quantum state, and you want, so this lives in the quantum world, but at the end of the day we want to measure these things to get some experimental output. And mathematically, this is modelized by a POVM, so positive operator valued measures. And in this very easy finite dimensional case, what is this? These are just a bunch of operators, k of them. These are d by d positive semi-definite matrices. So whenever you will see this inequality symbol, this is the positive semi-definite order. So these are positive semi-definite operators, and they sum up to the identity in this space of matrices. And why do we need these conditions? This is exactly what we need to ensure that the Born rule works. So the Born rule is the axiom of quantum mechanics, which tells you when you perform a measurement, what is the result of the measurement. So in quantum mechanics, measurement results are random. And this Born rule tells you what is the probability to observe one of these outcomes. So here you have k outcomes, and the probability to observe outcome I is given by the scalar product of psi and ai psi. Okay. And you see the positivity of ai's implies that these probabilities are non-negative, and the fact that the ai's sum up to the identity matrix and psi is of norm 1 implies that these probabilities sum up to 1. So this is precisely what you need. Okay? So that's a POVM. These will be central objects. I will be talking a lot about them. And now the main definition of this first part is the notion of compatibility of measurements. So now take two measurements, two POVMs, A and B. You see A has K outcomes and B has L outcomes. And these two measurements, A and B, these two POVMs A and B, are called compatible if there exists a third POVM, a third measurement, C, which now has K times L outcomes, and such that you can recover, sorry, there is some echo, maybe. Should put it a little bit, is it better? Or higher, good. So if, okay, so A and B are compatible if I can find a third measurement C, indexed by now, it has two indices, I and J, such that I can recover A and B by taking marginals of C. So outcome AI, so POVM element AI is obtained by summing over the J's, the CIJs, and the BJ is obtained as the other marginal, so I'm summing over the I's. And you see this definition, you can, so here I give the definition of compatibility for two measurements, but you can extend it to more than two measurements. So in this talk, I will consider a set of G measurements. They can have different number of outcomes. So in each measurement, you have K1 up to Kg outcomes. And the definition is the same. You have now this object C, which is indexed by, has G indices, and by summing all these over all these indices except one, you will get the corresponding POVM. Okay? So that's the definition. Now, let me briefly tell you why do we have this definition, so what does it actually mean in the real world. So as I told you, these POVMs, they model quantum measurements. So they model actually not precisely the physical process, but just the probabilities of the outcomes. So basically what happens is that you can imagine that what is a measurement, you have this green particle here, which enters this measurement device, and it gets destroyed by the measurement device. It gets eaten by this box. And when that happens, one of these K LEDs will light up, and then you will say, if the second one lights up, then you say, I have gotten outcome 2 of this measure. And now imagine you have G of these boxes, but only one particle, and you would be interested in measuring this, getting the outcomes for the G measurements, but you only have one particle, and as you might have heard, in quantum mechanics, you cannot clone particles, you cannot copy information. So what do you do? And compatibility is precisely that. What you can do is you have just one particle, you will put it in this larger measurement device C. You will get an outcome of C, and from this outcome, by doing some classical post-processing at the end, you will get you will actually simulate the measurement of the simultaneous measurement of these G devices. Okay? So compatibility is basically doing simultaneous measurements. And incompatibility is when you cannot do this. So when there is no such measurement device C which you can use to simulate the G things. Of course, the notion of compatibility appears in more general settings, but I will not talk about this. Okay, so now you have the definition. You have I hope, some physical intuition. Now let me formulate it as the way I like to think about this. It's this compatibility game. So how does this work? So you have two players, Alice and Bob. Alice has the measurement A on this A1, A2, A3. Here it has 3 possible outcomes. Bob has the measurement B. And basically what you want to do is, A and B are compatible. If Alice and Bob can fill out this 3 by 3 table with positive semi-definite operators in such a way that when you sum the rows, you will get the matrices AI, and when you sum the columns, you will get the matrices BJ. Right? So that's the game. That's what marginals are. You take row sums and column sums. And the important point, so why is this game interesting, is that you need to put in positive semi-definite operators. That's the requirement. So this object C has to be, so the entries of this table have to be positive semi-definite operators. And this is a shout out to Marek Bożejko's excellent talk from yesterday where he said that positive numbers are all that matter. And what I'm telling you here is that positive semi-definite operators are all that matter in this game. Okay? So that's what I call the compatibility game. You have the AIs and the BJs, and you want to fill this table such that row sums equal the AIs and column sums. If you sum columns, you will get the BJs. Okay? And it's, since I have this slide up, you can formulate, this problem is clearly what is called a semi-definite program. So you can solve it efficiently on a computer. But let me point out that if you have, here you have the example of 2 POVMs. Let's say you have G POVMs. The size of this semi-definite program will be 3 to the power G, because you will have to fill out this hypercube in dimension G with positive semi-definite operators. So if you have G measurements, it becomes intractable in the number of measurements. So it goes exponentially with the number of measurements. Just to say that in general, this problem is not, it's computationally not easy when you have lots of measurements. Good. So some examples, maybe to make things clear. So here's one case in which measurements are compatible. And in physics, this is how compatibility was thought of as commutativity for a long time. Oops. Thanks. So imagine that, consider the case where the POVM elements AI and BJ are commuting. So the commutator of AI and BJ is 0. then you can actually write down this joint measurement C simply by taking the product, the usual matrix product, AI times Bj. Because now if they commute, you can write it like this, and you can see you can write it as square root of AI Bj square root of AI, and this is positive semi-definite. So the fact that if the operators commute, you can do this simple trick. So commuting measurements are compatible. And if one of them actually, so there's a partial converse to this result, if one of either the AIs or the BJs are projections, then the converse is true. So in that case, commutativity is the same as compatibility. In the general case, there are different notions. And so let me show you an example of incompatible measurements. That's maybe the easiest one. So take the simplest Hilbert space, C2, and consider two bases. So the first one is the canonical basis, E1, E2. And the second one is this basis, which is like a 45-degree rotation of the canonical basis. So the elements are, 1, 1, and 1 minus 1, normalized. And consider the AIs to be the projection on the E vectors and the BJs to be the projection on the F vectors. Okay? So here is our compatibility game. You have to fill in this 2 by 2 square with positive semi-definite operators, such that when you sum the first row, you get the projection on the first element of the canonical basis. Second row, you get PE2, and the columns, you get the Fs. Okay? So let's look at this top left element. So what we have to put in there, the C11 element, this is a positive semi-definite matrix, which has to be smaller than, in the positive semi-definite order, it has to be smaller than PE1. That's a rank 1 projection, so then this matrix needs to be a projection, it needs to be a rank 1 operator, where the vector is collinear to, it's aligned to E1. And the same reasoning applies on the columns. So now you have a vector which is collinear to both E1 and F1. And there is, since they are not the same, they are not collinear, E1 and F1, this guy has to be 0. And the same reasoning applies to every element. So of course you cannot do this because every element has to be 0, so you cannot sum to something which is PE1, for instance. Okay. So clearly you cannot fill in this table in this situation, and because of course these are projections and they don't commute. So here's an example of incompatible measurements. Okay. And so if you have now two incompatible measurements, there is this idea that if you make them noisy enough, at some point they will become compatible. So that's a very important fact for me. So let me tell you about what I mean by noise and how does this work. So by noise, I mean you have a POVM, let's say a two-outcome POVM A1, A2, and adding noise means taking a convex combination between this POVM A and what is called a trivial POVM, which is just identity over 2, identity over 2. Okay? Because identity commutes with everything, so this is like the easiest example of a noise model. Okay? So adding noise means taking convex combinations with this trivial POVM. And if you do this simple computation, you'll see that if you start from any pair of POVMs, they might be incompatible. If you add noise 1/2, then you will render them compatible. And here's how this works. Simply define this joint guy Cij to be AI plus Bj. You have to divide by 4. And when you do, let's say, column sums of this Cij, you get half of AI plus half of this identity over 2. So for any A and B, the noisy versions with parameter 1/2 will be compatible. Okay? And now the question is, given any two pair of POVMs, how much noise do I have to add to them in order to make sure that they become compatible? And that's the main definition of this first part. It's this set, this compatibility region. So what is the set? So this is a set of G tuples, such that if I take any G tuple of two outcome POVMs, so I'm now focusing on two outcome POVMs. So all my POVMs will be this yes, no, so they will have just two elements of the form, E and identity minus E. So I take a G tuple of such POVMs, and I want to make sure that if I add noise 1 minus Si to the ith POVM, then the resulting objects are compatible. Okay? And you see this will be, it's easy to see that the set gamma GD is a convex set. And it has two parameters. Let me mention this once more because this is important. So G is the number of measurements, and D is the dimension of the Hilbert space. And here are some properties, some easy facts about the set. Well, as I said, it's convex because if you have two elements, you can just take the convex combination of this P of EMC, which is so it has these points of the of the form 1, 0, 0, 0, and all the basis elements are inside the set gamma GD, because if I consider Si to be 0, then so for instance 1, 0, 0, 0 belongs to this element because I'm just taking the first P of EM and the other ones will be trivial, so these are commuting, so they will be, of course, they will be compatible. So actually in the set, so here I took G equals 2, so you have this, by convexity, you have this whole triangle, this whole dark blue triangle, which is contained in this compatibility set. And that's kind of a trivial fact. What we want to do in quantum theory, we want to understand if we have more, if we want to understand this light blue part. So how much more this triangle can be extended. And you know that the point 1, 1 in this set, so the point here, the point 1, 1, is not included in the set because you have incompatible measurements. So if you take a pair of incompatible measurements, like the ones I showed you before, then basically you're not adding any noise. So this means that the point 1, 1 is not in the set. And the question is, how far this set extends above the triangle. This is what this will be our final goal, to understand this set. And also let me point out that this set is a set which is kind of fundamental to quantum mechanics. So you see it only depends on two parameters, and it tells you how much incompatibility you have in quantum mechanics. So this is, you can see incompatibility like a resource. It's a non-classicality. It's a measure of non-classicality. So you want to know how, what are, for instance, the most incompatible quantum measurements. So this is something which we like to understand. Okay, so that wraps up the first part. Again, the goal is to understand this incompatibility set gamma GD. Good. Now let me switch gears and tell you about something completely different. I'll tell you about free spectrahedra. Okay, so sorry about the experts in the room who know about this, but I think it's not yet a standard notion, so let me spend some time telling you about this. So first, the starting point is these convex polytopes, polyhedra. And there are two kind of dual ways to define polyhedra. One is to say that a polyhedron is the convex hull of finitely many points. And the other one, and that's the one we will take here, is to say that a polyhedron is just an intersection of finitely many half spaces, affine half spaces. So here's the definition. You see you have a subset of R to the power G. This will be the same G as before, the number of measurements, but now it's just the dimension of the space, of RG. And this polyhedron is defined by asking that the points inside should satisfy this affine, should be on one side of this affine hyperplane. So the polyhedron is defined by these vectors h1 up to hk here. Okay? And the hi's kind of corresponds to the facets of my object. And you see the idea is that now I define this polyhedron by taking some inequalities, asking that some kind of linear inequalities are satisfied. And a spectrahedra is kind of the same thing, but I'm asking now that I'm replacing this order here, which is usual order, numbers, real numbers, by the positive semi-definite order. So, and this is the notion of spectrahedra. So what is a spectrahedron? It's a set of points in Rg such that the following linear matrix inequality, the following LMI, is satisfied. So I take a linear sum of some operators AI and ask that this operator should be smaller in the positive semi-definite order than the identity matrix. So the spectrahedron, which I denote dA of 1, the one will be clear in a moment, is defined by this tuple of matrices, A1 up to AG, and these are D by D matrices. Okay? But the object itself lives in R to the G, and is defined by this G tuple of D by D self-adjoint matrices, A1H. Okay? And I'm putting this A here to say that this is the tuple which is defining the object. And so now what happens is that if you take diagonal matrices and you think for a minute, then this linear matrix inequality is just a bunch of normal inequalities for the coordinates. So you will get a polyhedron. So if the matrices AI are diagonal if they commute, then you get back polyhedra. But if they don't commute, you get more general convex sets. Here is a famous one. In quantum information, this is the Euclidean ball in R3, which we call the Bloch ball because it's the state space of a quantum bit, of a qubit. And this is the spectrahedron, which is defined by these three Pauli matrices, sigma x, sigma y, sigma z. And if you have x, y, z real numbers such that this inequality is satisfied, this is equivalent to the norm of the vector x, y, z being smaller than 1. So this precisely defines the unit ball of R3. Okay? So you see, you get more general objects. You get objects which have infinitely many extremal points. You get rounded objects. Yeah, that's just a picture. Yeah, it's different. It's not a ball. I have no idea. I copy-pasted this picture from somewhere. Yes, I should add citation to my pictures, but yeah. Yeah, I think it's Wikipedia or I don't know. But it's a spectrahedron. Of course, not every convex set is a spectrahedron. But these are the objects that we are going to be interested in. And when you do operator theory and you see this kind of object here, what you want is to, especially if you come from quantum theory, you see this product here xi or ai, and you want to replace it by a tensor product. And this is how you get this notion of free spectrahedra. This is where the word free comes in. So a free spectrahedron is just a collection of these what are called levels of a spectrahedron. And these levels are, basically it's the same formula you had here. You just replace the numbers xi by matrices capital Xi. Okay? And you replace the product with a tensor product. So the nth level of the free spectrahedron defined by a G-tuple of matrices A. So A is fixed. And once I fix A, these are d by d matrices. For each integer n, I will have this convex set, dA of n, which is a set of G-tuples of n by n self-adjoint matrices, which satisfy this inequality. Again, this is the positive semi-definite order. And I take the collection for all n of these sets, and this is what is called the free spectrum. Okay, so this is a collection of convex sets, and at each level I have G-tuples of matrices. That's my definition, and this is what this paper of Bill Helton and collaborators was about. And here are some examples. So Bill's paper was about the matrix cube. And that's maybe the one of the most famous free spectrahedra because it has some applications to combinatorial optimization. I will tell you in a moment how this works. And so what is a matrix cube? So this is a free spectrahedron, which is defined by some matrices. I give you the matrices are here. It's defined by this tuple of matrices K, which are diagonal matrices. But it's not important. What's important is that at level, why is it called a matrix cube? Because at level 1, it's the hypercube. So at level 1, it's the hypercube in RG. So it's the unit ball of L infinity norm. And at level n, it's just G-tuples of matrices, so G-tuples of contractions, self-adjoint contractions. Okay? This looks like a matrix hypercube, if you want. And the one actually that is connected to the first part of the talk, it's kind of dual, which is called the matrix diamond. And why do I say that it's dual? Because at level 1, at level 1 is a convex polyhedron, which is the unit ball of the L1 norm. Okay? So it has, two G extremal points, these plus or minus EIs. And at level n, this is definition, you require that all sign sums of the AIs should be smaller than, of the XIs, sorry, should be smaller than the identity. So for all possible choices of signs. And you see, if you think about it, it's the same with you have this duality between L1 and L infinity norm, and you see that, the L infinity norm, the hypercube, has lots of extremal points, has 2 to the power g extremal points, so all sign vectors are the extremal points of the hypercube, but it has few facets. It has just 2 times g facets. And for the L1 unit ball, the situation is reversed, so it has few extremal points, 2g extremal points, but lots of facets. And the way to go from the polyhedra to spectrahedra is just to work with this, with facets, so you define them by inequalities. So this is why the matrix diamond has lots of inequalities, defined by lots of inequalities, precisely 2 to the power g inequalities, where here you just have 2 times g inequalities, okay? So keep that in mind, matrix diamond, you have lots of inequalities, 2 to the power g. Okay, so these are the examples that, that I'll be interested in, and especially the second one, so this matrix diamond. Now, as I told you about previously, I told you about this problem of adding noise to measurements. And you will see in a moment that the corresponding notion in this spectrahedral world is the problem of spectrahedral inclusion. So what is this? Basically, it's just asking whether one spectrahedron is included in a second one. So you see, I have to consider now 2 spectrahedra. These are defined, these live in the same, they give you, the 3 spectrahedra live in the same space, so they are both defined by G tuples of matrices, A1, AG, and B1, BG. But the size of these matrices can be different. Okay. And we say that the spectrahedron defined by A, the A is contained in dB, if you have inclusion for all levels. For each n, you have the A of n included in dB of n. And the game that we will play is the following one. I will look at 2 spectrahedra. Of course, if I have inclusion at all levels, I have inclusion at level 1. But the question I'm interested in is the following one. Suppose I have inclusion at level 1. This inclusion might not hold at higher levels. And the question that I'm asking is, given that I have inclusion at level 1, how much do I have to shrink the first one, the A, such that it fits at all levels inside dB? Okay? So this adding noise in the first part is this is the equivalent notion to that. And now I define a new set called delta. Delta only depends on A. And it's the set again of G tuples of weights, Si, such that for every G tuple of matrices B, assuming that I have inclusion at level 1, the A of 1 included in dB of 1, then by shrinking the spectrahedron, the free spectrahedron di by S, so I'm shrinking the first matrix by S1, the second one by S2, and the Gth matrix by Sg, then I have inclusion at first level. So again, I have inclusion at level 1. How much do I have to shrink the first guy in order to have inclusion at all levels? And again, this set has now 2 parameters again. So G is the number of matrices, the number of A matrices defining spectrahedra, and D is the size of the B matrices. So I don't want to consider inclusion for all spectrahedra dB here. I just want to restrict to spectrahedra which are defined by matrices of size B. So you can think about this small d as the complexity of dB, because the more parameters I have in B, the more complex the geometrical object will be. Okay? And as I told you, so this paper of Bill Helton, this is, if you think about this problem now, if A is the matrix Q, inclusion at level 1, so I have to check whether the hypercube is contained into a larger spectrahedron. And you see, to check this, you have basically just one option is you have to check that every extremal point of the hypercube is inside this dB of 1. And you see, you have to check 2 to the power g points. So that's computationally hard. And however, this, as you'll see in a moment, this free spectrahedron inclusion, it's a much simpler problem. And the paper of Bill was asking, if it's basically what is called an SDP relaxation of this hard combinatorial optimization problem at level 1 to a much easier one. And when you have these relaxations, you're interested in how much you lose. And that's this is basically what's encoded in the set delta A. Okay, so now whenever I will talk about the spectrahedron, which is the matrix diamond, which is defined by some matrices A, I will not write the A, and so the inclusion set for the matrix diamond, I will just denote it by delta of GD. So as I told you, the matrix diamond is the spectrahedron, which is the one I'm interested in. Okay, and of course, so again, since you have this duality, it's the same as the one for the matrix cube, and the one from the matrix cubes has been studied in this paper of Bill Helton, and other people have looked at these. So this made our life much easier. Good. So I've told you now 2 stories. Let's connect them in this third section. So here is our main result. So basically, this is the slide which has maybe the main theorem, and then once you have this main theorem, you can basically all the other things follow. So let me tell you about this main theorem. So start from a G tuple of operators E1 up to EG. This can be anything. These are just self-adjoint. Okay. And you defined. You look at the spectrahedron, which is defined by the matrices 2EI minus identity. I have to shift them and rescale a bit to make things work. So this is the definition. These are the set of all matrices G tuple of matrices X, such that you have this inequality here. Okay. And here is the theorem. So first point is that these matrices E are quantum effects. Remember, a quantum effect is just one element of a P of EM, so it's a matrix between 0 and identity. So 0, so it's a positive semi-definite contraction, self-adjoint contraction. So the EIs are quantum effects if and only if you have inclusion at level 1. That's a one-line proof, because inclusion at level 1, you just have to check the extremal points of the diamond, and these give you precisely the inequalities. This matrix is between minus identity and identity, and that's precisely what you need. Okay, that's kind of trivial. So this connects level 1 inclusion of the matrix diamond in the spectrahedron defined by E to the fact that the E's correspond to quantum measurements. Now, the key point is this second one here, is that moreover, the E's are compatible quantum measurements if you have inclusion at all levels. So if I require inclusion at all levels, this is a stronger notion, and this corresponds in the quantum world to not just having measurements, but compatible measurements. So then there is this, we can also characterize this intermediate level inclusion, but I don't want to spend too much time on this because maybe it's not so important. So you have this equivalence. So this is like an equivalence theorem. We have just, say that 2 things are the same. But maybe the more important point is that you also have equality of this compatibility region, gamma of GD, to the inclusion set of the matrix diamond, delta of GD. Okay? So not only I have equivalence here, but I have also this noisy version are also equivalent. So the amount of noise I have to add to measurements to make them compatible is the same as these inclusion constants, which remember are how much do I have to shrink one spectrahedron such that inclusion at level 1 implies inclusion at all levels. Okay. And here I've told you the story about these dichotomic measurements, so measurements, quantum measurements with just 2 outputs, but the same result holds in a more general setting. You just have to replace this matrix diamond by a more complicated spectrahedron, which we decided to call the matrix jewel, because it's like a fancier diamond or whatever. Good, so that's our main theorem. So here now, of course, we have established this connection between 2 fields, and then we looked at the literature, what is known about compatibility, what is known about free spectrahedra. So people have worked a lot on these inclusion sets, especially in the case where where these weights SI are the same. So in the paper of, I think this is the paper of Bill Helton, so they have shown, for instance, that the set contains some particular points. And Passer and collaborators also have shown that actually the unit ball of the Euclidean ball is contained in this inclusion set. So we have lots of results about the deltas coming from the literature about free spectrahedra. We also have in quantum information, people have thought a lot about this compatibility problem, and they also have many results. So in small dimension, for small GND, they have computed basically case by case this incompatibility region, and they also have many techniques which come from the intuition of quantum theory to give bounds on these sets. And one of them is this quantum cloning. This quantum cloning idea is that, again, you cannot perfectly copy quantum information, but you can, if you allow some errors, you can approximately do this. And this is about quantum channels. Marek Božek also mentioned quantum channels, and have used these ideas to give bounds on these sets. And also with Andreas, we have seen that this is also connected to some tensor norms, so to this inequality between injective and some fancy tensor norm. So there's like many approaches coming from the quantum side to this compatibility idea. And when you put all these ideas together, basically we were able to solve our initial problem in one setting, and the setting is when you have G measurements, but you need your Hilbert space to be large enough to be exponential in G. So whenever this happens, when your Hilbert space is large enough, then we have computed exactly both of these sets, so incompatibility and inclusion constants, and these are precisely this what we call the quarter circle, so the unit ball of the Euclidean ball. Okay, this is precisely what I mean. Basically, we showed that this passer bound is precise. Okay, and however, we need this condition. So we need that the Hilbert space is large enough in order to accommodate for some special objects. I will tell you. I only have a few minutes. I will tell you about maybe about these objects. So yeah, so we have solved this problem in this case. So let me tell you now. I have maybe take 5 minutes to give you some proof ideas. So basically, the workhorse of this this project is this result by Helton and collaborators, which tells you exactly what spectrahedral inclusion means. So you have two spectrahedra A and B, some technical condition that the first level of the A spectrahedron is bounded, but this is just to ensure that the following map, so you consider the following map, phi, which is defined on an operator system defined by the AIs. And this map is defined by sending AI to BI and unital, so it sends identity to identity. And you have inclusion of the A into the B at level n, if and only if this map is n positive. So it means that when I tensor this map with identity on n by matrices, I get a positive map. And once you have this theorem, then everything is kind of easy. So level 1, as I told you, is very easy because you just have to check these extremal points of the matrix diamond. There are 2G of them, and you get the inequalities. And now the free level. So this map basically. So these are the matrices which define the matrix diamond, and you're asking that the map which maps this matrix here to 2EI minus identity is completely positive, and then you just use an extension theorem to extend this map to the whole space, so to R to the 2 to the G. And once you have this extension phi tilde, if you look at phi tilde, this is given magically by the Arvesson extension theorem, somehow you can connect this phi tilde to the joint, to this joint measurement C, which I was telling you about on the first slide. So basically, Arvesson's extension theorem gives you this joint measurement if you have free spectrahedral inclusion. So that's basically one of the ideas of the proof. Now let me tell you, I mean, the other thing that I wanted to tell you about, to keep things light, because it's the last talk and I don't want to go over time, is about this example that I was telling you about. And this example, on the quantum information side, this corresponds to the most incompatible G-tuple of measurements. And you get these measurements by using this construction, which appears all over the place in mathematical physics under many names. You can see Clifford something or spin system, or has many names depending on where it's used. And this construction tells you that in dimension 2 to the power k, you can find 2k plus 1 self-adjoint unitary operators. So these are self-adjoint operators which have eigenvalues plus minus 1, which are anti-commuting. So I call them this f1 up to f2k plus 1. And you cannot do better. So if you want 2k plus 1 such operators, they only exist in Hilbert space of dimension 2 to the power k. And this is why, to prove this, to prove the result I was telling you about earlier, we need this large Hilbert space, this exponential Hilbert space, in order to accommodate for such matrices. And the way, there is an explicit construction. You just iterate a construction using Pauli matrices, as usual. It's one of the best ideas to take tensor products of Paulis are very important. And so how does this help us? These matrices have this very nice property that if you take a linear combination of them, then the operator norm of this linear combination is just the 2 norm of the coefficients. So that's one thing. And if you take a linear combination of fi tensor fi bar, then the operator norm of this thing is the 1 norm of the vector x. So it's a much larger object. And if you looked at some quantum information theory, then you will immediately recognize that this is the type of thing that we encounter a lot. So we're very happy to have such objects. And once you have these matrices, you turn them into measurements by doing some easy translation. Okay, that's all I wanted to tell you. Here is a recap again of the ideas that I wanted to tell you about. So, measurements, again, positive semi-definite operators which sum up to identity. And we have this particular class of measurements called compatible measurements. And these are the ones which can be obtained from a larger measurement by taking marginals. And that's quantum information side, free spectrahedra side. So spectrahedra are just generalizations of polyhedra, so they are defined by these inequalities. But now you have positive semi-definite inequalities. And the one which we like is the matrix diamond, which is a free spectrahedron defined by this particular set of inequalities. So signed sums of matrices xi. And this is the main idea of our work, is that if for some operators you have inclusion of the matrix diamond at level 1, then these operators are associated to quantum measurements. And if you have inclusion at all levels, then these operators are associated to compatible quantum measurements. And not only that, but we have these noisy versions also. And just briefly, I wanted to tell you that the other famous free spectrahedron, which is the matrix cube, is connected to a different problem in quantum information, which is called steering. And now with Andreas, we are looking at another free spectrahedron, which at level 1 is the Birkhoff polytope. And this again has some counterpart in quantum information theory, but that's for another talk. So thank you very much for it.
Thank you very much. We have a lot of time for discussion. Who would like to ask a question or make a comment? Please. Wow, so let me make some comments. You worked also on those quantum Latin squares, and there were some papers on magic squares by De las Cuevas and Netzer. I'm not sure whether he is here. So in the special case of compatibility, if all those operators are the same, then your square of compatibility corresponds to just such a block matrix of operators such that all of them are positive and there's some column-wise and row-wise to unity. So then in your language you can say that if you make a ball around this point, all those operators are compatible, yes?
Yes, exactly, yeah.
And do you know what is the radius of this ball for higher dimensions? It goes down or up with dimensionality?
So I think it goes down.
Down. Mm-hmm. So this ball will be smaller and smaller?
Yes. So basically what happens, I showed you this picture at the very beginning with this compatibility region. So you see, when the dimension d goes to infinity, the quantum part, this light yellow part will converge to the triangle. So basically, in large dimension, you have so much incompatibility that you can only do these classical things. You cannot.
Yes, yes. So like the relative volume of a simplex inside the ball is smaller and smaller.
It's smaller and smaller. You can, yeah.
Thanks. Thanks a lot. Any other questions or comments? Please. Well, it looks
Since
it's
I'm
not
the last
case.
speaker, I would like to make a comment and thank the organizers of this conference for this beautiful event. So we should all thank them. Thanks a lot.